So now let's talk a little bit about wave motion. So wave motion, one way you can kind of consider this is if we take our unit circle that we had before and we roll it along some surface, then what we'll end up plotting is a sinusoid. And so this is one way of viewing wave motion. And wave motion is everywhere, from molecular vibrations and sound waves, and it describes a lot of different physical phenomenon. So it's incredibly important to know, and we'll find out that electrons can be described by a wave. So that's an important concept to grasp. So we need to come up with a function that describes some motion, some wave-like motion. And so let's say that the amplitude, we want this to change with position, and we also want it to change in time. So we want it to be moving. We want it to be moving in some direction over time, and we want it to have some position along that, and then we'll call that the x. Alright, we also don't want it to be unit height. Now that's what it would be if we just kept it as a sine wave. We want it to be any amplitude, so we define some amplitude here. So we're going to have a sinusoidal wave. It's got to be a function of time and of position. So we can write A0, so this is some number that we can times our sine wave by, and this here is our amplitude. And we saw this earlier for the example of pressure versus volume, that we get some sort of you can kind of think about it as a multiplication factor out front that was scaling our 1 over v function. But in this case, this A0 scales our sine wave. And we're going to need something that changes as a function of time, and so we'll just describe some constant. Some constant doesn't have to be. We can some constant. It's called the angular velocity, and that is time. That's the time component, and we'll subtract off another constant k times x, which is our x variable, and we'll add on to that what's called a phase factor, and this is the Greek symbol phi, and it basically tells us where the wave starts. So let's try, and this is quite a complicated thing, and we've people made this up in order to describe wave motion. So let's see what all these different parameters describe. So let's take time as equal to 0, and so basically that will mean that this term goes to 0, and we'll just have this minus kx plus phi term. So if we draw this out, it's not moving in time, so the wave sorry, I'll just go. Okay, sine always starts at 0. This here is our phase shift, phi. This here is our amplitude, A0. And this here is what we say is the wavelength. Okay, the wavelength. And the wavelength is related to this x component here, but we have to convert it into an angular unit because this sine function only takes in angles. So in order to convert it, we just divide it. We go 2 pi, which is the circumference of a circle, a unit circle, and we divide that by lambda, and that is equal our k. And this is our k number, or our wave number, and this describes the meters per radian that we're traveling. the radians per meter, because if you look at the units, you've got radians up top because it's converted into radians by this 2 pi factor, and it's the units of lambda are in meters usually. Okay, so this is at time is equal to 0. So as we go through time, what is going to happen is we're going to have this factor here that is going to add or subtract to our angle inside of here. So this is kind of like how the angle changes with time, and what that does is it basically gives us a shift in time, or actually always a positive shift if this is negative, and so it will move any position we've got over time along a certain direction. And so this is what we mean by a travelling wave. A travelling wave is something that has some sort of shape in space, and it moves along at a certain speed with time. And so what we call our omega is our angular velocity. And the units of it are radians per second. And so we've got this repeating unit of this wave, and that's what's called the wavelength. So it goes all the way around and it comes back up, and basically the phase has gone around once the circle. That's one way of viewing it. Sorry. It goes around that way. Yep, so it's gone around once the circle, and so you get this here as basically the wavelength is determined by when the unit repeats, and we can describe how long it takes for this wavelength to pass a certain point, and that's called the period. And so the period is the time it takes for us to travel one wavelength. And we describe our this is called our period. Oh, it's going very slowly. There we go. And that's going to be equal 1 over our frequency. And so this period is in seconds, and so omega is going to be equal to 2 pi divided by t, but according to this relationship here, we can also write it as 2 pi times the frequency. And frequency is in units per second. So this tells us how long it takes how many seconds it takes for one wavelength to pass, and this tells us in 1 second how many wavelengths pass. And so that's the difference. This is per wavelengths, this is per seconds. So we can describe our velocity as equal to the distance divided by the time. That's kind of a common way of describing the velocity. So meters per second. And so we can kind of think about this as the wavelength, which is in meters, and the time in which it takes for one wavelength to pass, which is our period. And we can write that as f lambda. The velocity of a wave that's traveling in vacuum of light is c, which is 3 times 10 to the 8 meters per second. That's really, really fast. So you can start to think about if you've got a wavelength, say of 400 nanometers, then the frequency at which it has many oscillations every second. So it oscillates so quickly that we actually have no detectors that can measure that. Incredibly fast. So let's look at another way of viewing the velocity, and that's equal to the angular frequency divided by the wave number. And so I'll just try and explain how that works using units. So this is it's a proof that I'm doing using units. So this is why units are so important to know. Omega over k is equal to, let's look at the units. The units are for omega, it's radians per second, and down below for k it's radians per meters. And so the radians cancels, and we've got seconds over meters. Alright, and so we can write this out as 1 over s, that's what this thing is, to the power of -1, and we're dividing that by 1 over m. Now when you divide fractions, you flip the second fraction and you multiply. So I've got 1 over s times m over 1, and then we times the top and bottom, the numerators and the denominators, and we get meters per second. So you see that the velocity is the exact same as going the wavelength divided by the period. So that's one way to work that out. The negative kx in the form of it means that the wave is traveling to the right. Okay.